what this method allows us to do is use this recursive formula, fancy word, recursive formula to determine the roots of a function. So it's a calculus-based technique that allows you to determine the roots of a function without actually solving an equation, right? So it just seems like it's probably unnecessarily complicated when you do it by hand. But once you involve technology, you see how it ends up being kind of the shortest distance between 2 points, right? It's actually a brute force technique that we use to come up with solutions. In fact, this is the underlying software or the programming, the code behind the software in your calculator for finding roots, intercepts, and things like that. All right, so when you actually use the intersect function or the zero function on your calculator, it's doing this, which is a kind of a cool thing to think about. All right, so what are we actually doing here? We have x sub n plus 1 equals x sub n minus, I mean, I could just read the formula, but it doesn't really tell us much. All right, so I'm going to write it out again and just kind of point to some stuff. All right. First thing you should notice when you look at it is that there's a prime in there, which means derivative, obviously. I don't think it's unfair to say obviously. We've been working with that all year. So my original function, f of x equals x squared minus 2. So my derivative function, f prime, would be 2x. All right, so that's a place to start. They also tell us that we have a key fact, and it's very key. They tell us that x sub 1 is equal to 2. All right, so let's actually start with that piece of information. X sub 1 is equal to 2. And in fact, let's just even focus a little bit more. Let's just take a look at the x sub 1 part of it. I don't know. I don't understand this highlighter technology. It's not, like, what's the point of that? Like, it's just erasing it. It's blurring it out. All right, well, pretend I highlighted it, and it looked great. So, x sub 1 tells us that the n value, I still have the highlighter on, the useless highlighter, that the n value is equal to 1. All right, if that's the case, x sub 2 would be equal to x sub 1.
Are you done with your test already?
Oh, we're in the test. I'm in the bathroom.
Yeah, dude. That's so my fault. I'm going to move for you. Okay. You know that?
Thank you.
Dude, there's no problem. You just might want to, like, move the row.
That's a foul.
Unless you want to, like, really be close to each other. You look nice.
Yeah, I'm sure that's going to work out nicely for me. So, not really sure one way or the other, but it's going to happen. So if I plug in a 2, because based on a notation here, if I designate if it's x of n where n is equal to 1, then everything on the right-hand side, every instance of n is going to be replaced with a 1. On the left-hand side, it's n plus 1, so that would become a 2. Since I know x of 1 is equal to 2, the right-hand side is going to clean up somewhat and give us 2 minus f of 2. Okay, so f of 2 would be what I would get when I plug a 2 in here. So 2 squared is 4 minus 2 is 2. And on the bottom, I'm looking at f prime of 2. All right, so that's what I would get if I plug a 2 into my derivative, which would be 4. So 2 minus 2/4, which is the same as 2 minus a half, which is going to be 1.5, 3/2, 1.5, however you want to write it. We'll go with decimals here, because when I show you the calculator technique, it's going to be in decimals anyway. All right. So that's our first result. Now you can see the table here contains more than one empty cell. I'll come back to that in a sec. So I'll pop a 1.5 in there, knowing full well that I have to do, if I were doing this whole thing by hand, I would have to do 4 more calculations. But then 4 more calculations of what? Well, the next entry would be where n is equal, oh, that's lovely. N would be equal to 2. So that means that I'm looking at x sub 3 would be equal to x sub 2 minus f of x sub 2 over f prime of x sub 2. All right, so what that's telling me, and this is where things start getting a little out of hand. You're probably not going to like it too much. But when you realize that you'll never have to do it by hand after this, then you start to come around. X sub 2 here, all of these x sub 2s, they're the result of our first calculation. Because my first calculation gave me x sub 2, which is 1.5. So that's telling me that I have to replace every x sub 2 with a 1.5. So 1.5 minus, plug in the 1.5 to my original function. 1.5 squared is 2.25. Because 15 squared is 225. Minus 2 is 0.25. So 0.25. On the bottom, it would be 1.5 times 2, which is going to give me a 3. All right. Calculation-wise, it's still not terrible, but it's not something that you really want to be doing. Because, again, you're looking at the table. After this, there's 3 more cells to work off of. 1.5 is the same as 3 halves. This would be the same as 1/12. 3 halves, if I made it a denominator of 12, it would be 18 12 minus 1/12, so 17 12ths. And that's only because I don't want to walk over there to pick up my calculator. So whatever the decimal is equivalent to 17 12ths. So 17 12ths or the equivalent decimal. All right. So at this point, you've lost any interest in continuing the process because if you kind of follow the trend, the next iteration would involve us taking the 17 12ths and plugging it in, complicated calculations. I'd have to square 17 12ths. 389 over 1. I don't even, I lose it sometimes. 17 squared is what? 289. Off by 100. Then I'd have to subtract 2, and it's a mess. All right, so I don't want to do that. What I do want to do is go to my calculator and just be so happy. Just so happy that if I were in your place, that I have a teacher who, during his lunch period, enjoys writing programs. Because you have a nice one in there. Assuming you didn't clear them all out, there's something you keep.
That actually happened to me today.
My thing, it was like freaking out, and I just had all these like random pixels. And
so you're like, let me just clear it.
No, I didn't clear it. I took out a battery, put it back in, and it just says RAM cleared.
Okay.
And I got mad. I got very
Fix
mad.
that later, but for now,
Thank you.
no problem. So program. In your program list, you should have one that says Newt, which should make sense because it's called Newton's method. You know, I promised you way back when that there was a bunch of programs that I was dumping in your calculator. We weren't going to use damn near any of them for a while, but then all of a sudden we were going to use all of them. In the next month, we will have used every single one of the programs that I dumped in there, and you'll be thankful that we have programs for it, I promise you. All right, so select Newt. Program Newt, hit enter. It asks you for y1. Y1 would be whatever the original function is. In this case, x squared minus 2. So type in x squared minus 9. Hit enter. It asks you for an initial guess. It's a weird phrasing. Initial guess sounds like it's very imprecise. Like, oh, all of a sudden we're just going to guess. We've done all this math. Like 4 years of high school math, and now all of a sudden we're resorting to just guessing. That sounds like fun. In this case, they gave us the guess, the quote-unquote guess, which is 2. So we would put that in. But what this is actually is, I mean, it's surprising to think of it this way, but it actually is a guess. I have no idea what the roots of this equation are. So I'm just going to take a guess. The iterative process here, Newton's method, through the cycling of calculations, taking the answer from one, plugging it into the other, spiraling out from there, eventually draws you in to the nearest solution to whatever your guess was. Right? So if I had 5 possible solutions, whatever my guess was, Newton's method is going to drag me to the closest solution to that guess. All right? Which is good and bad. It's bad because if there are 5 solutions, it's only going to give me one at a time, and it's going to be dependent on my guess. If there's only one solution, that's great news, like a linear function or something like that, because what it's telling me is that it doesn't matter what I guess, it's eventually going to take me to the correct answer. All right, so they're saying 2, so I'll put it at 2. Hit enter. Oh, look at that. It's crazy. It's like the program knows Newton's method. Less satisfying because I never calculated what 17/12 is.
It's the same.
But it is the same. All right. The next entry would be if I were to take the 17/12, plug it back into the formula and run the calculation. Then the 5th one. Let's see.
It's the same number.
Same, well, very close. It isn't until the last one where it becomes exactly the same. And the way I wrote the program was so that if there were any, if you ever get any 2 consecutive iterations that are exactly identical, the program stops because it doesn't matter how many times you run the program after that or you run the calculations, you're never going to get closer and closer to a solution because you're already there. All right? So all you'd have to do at this point is just jot these numbers down and state that our final answer is whatever the repeated value is. If I hit enter one more time, it says done because I do have that repetition. I have it coded in here so that if there's equality, it's an if-then, it's a conditional. And if you actually just look through the coding, you can see the conditional. If these 2 things are equal, stop because we're there, we have our answer. All right? So it's telling me my solution is 1.414-ish. All right. If you were to solve this equation, we're looking for roots, right? Solve an equation by setting it equal to 0 and solve, you get the roots. If I were to set this equal to 0 and solve, I get x squared equals 2. Take the square root of that, I get plus or minus root 2, right? What's the square root of 2? 1.414-ish, right? So it just told me that the square root of 2 is my answer. But it gave it to me in decimal form. This whole unit is about approximations because analytic approaches, exact values are wonderful, but sometimes an approximation gets the job done and that's all we need, all right? So then the big question would be, all right, well, there is a negative solution. How would I come about that? Run Newton's method again. So x squared minus 2. Make a different initial guess. Something that will not drag you to the positive solution. So what I need is a solution that is closer to the negative one than it would be to the positive one. So all I need is something on the other side of the negative solution. If you're in doubt, make it extreme. I'll put it in negative. Let's say I have no idea, but I want it to pull me to a negative solution. Negative 100 is a pretty safe bet. You might have to hit enter a few more times, but eventually it drags you closer and closer.
So your initial guess really doesn't matter.
The initial guess doesn't matter as long as it's closer to the solution you want than it is to the solution you don't want.
Meaning negative and positive.
Correct.
Okay.
And you got to be careful because if it's like a cubic, you could have 3 solutions. So you might have 1 negative, 1 positive. Actually, you might have 2 negative and 1 positive. It could break down in a bunch of different ways. So you might have to test a bunch of different values before you get to the most number of solutions that you could have. But there's no algebra involved. You get the answer. And that's the same. That's what the calculator is doing. Every time you graph it and you select 0 or intersect, it's doing that work. It's just not showing you the work. It's happening in the blink of an eye. Not even.
I'm just wondering, so like when you're doing this, if you were to have started with like, well, this is negative inside puzzles, so, but if you did like 100 and it gave you all of these numbers, would you just want to keep doing it until you got one that gave you the least amount of steps? Like, is that what you're going for?
Not really. I mean, ideally that would be the case because that would mean that you have a good intuition of what the answer is, you know, going into it without doing any work. Like that, as a student, you're saying, I have a feeling, a good feeling that it's around 2. That's showing that you have a good grasp sense of the situation. If you put in a 100, it's because you have no idea what the answer is and you want it to do the work. This is a brute force strategy. And if you think about the real world, brute force technological strategies are at play all the time. I mean, if you think about it, anytime you get a phone call that's from one of those robocall things, that's brute force. They're just dialing numbers. Apparently it costs them 1 cent for every call that they make. But the return is on average $430 per received phone call.
How? And who
Because
doesn't hang up on them?
For every person like me who either doesn't answer it or answers it and tells them something funny, or at least I think it's funny, it's probably horrifically offensive, but I mean, anybody listening, they always laugh, so I'm sure it's hilarious to someone. For every person like me, there's some schmo that dumps like 10 grand, and it's like, all right, cool, good for you. I mean, oh, and by the way, whenever you get one, I was reading up on this because I got my son a phone, and immediately after he got the phone, he started getting the robocalls. I mean, he's 8 years old and he's getting robocalls. I'm like, because he does after school activities and he just get picked up at weird times. So it's communication. That's my reason. His reason is games. So it should sound familiar. And I guess social media now for you. But yeah, he would get those calls immediately. So I started reading up on it. And so it costs them next to nothing to make the call. They get a good return on it, but it's all automatic. So they have software that just automatically dials. When you answer, if you do, never say the word yes. So they'll say, are you the head of the household? If you say yes, they've recorded your voice to use it as assent for when they commit fraud on you. I had no idea about any of this, so now I know.